Hello everyone, this is Hijikata from Saitama University. Today, I would like to talk about the mysterious quantum phenomena appearing in quantum world. The title is Mystery of Parallel World Appearing in Quantum World. Okay, let's start. This is the outline of the lecture. Firstly, starting with what is quantum, then reviewing Young double-slit experiment, and regarding this experiment, describes the wave and particle duality in quantum physics. Next, one was symbolic quantum physics research, delayed choice quantum inertia experiment will be introduced. Finally, mention various applications from quantum optics. Firstly, I would like to talk about what is quantum. According to the Japanese MEX website, quantum is the smallest unit of matter, or smallest energy that possesses both particle and wave properties. For example, electron is the smallest particle that makes up matter and the smallest unit of electric charge. And photon is the smallest unit of light. Before explanation of quantum physics, I'd like to mention the famous light wave experiment, so-called Young double-slit experiment. Double-slit experiment is composed of two slits and a screen far from the slit. And the plane wave, monochromatic light, for example, laser source is incident to the slit. Since the light passing through the two slits interferes with each other, a stripe pattern appears on the screen. This animation shows a demonstration of a double-slit experiment. We can see the two light waves coming from different slits interfere with each other. So the waves create constructive and destructive waves in some areas, forming a striped pattern like this. By the way, what would happen if the light source were replaced by quanta, such as electron beam or single photons? In this case, there should be no interference. Interference should not appear. But is it correct? The answer is no. Surprisingly, although quanta are kind of particles, interference fringes are indeed observed to be projected. One might consider if particles interfere with each other, how would be observed the path the particles took? Namely, what would occur if we observed which slit quanta passed through? Consequently, upon observation, the interference fringes vanish and are replaced by two distinct bands like this. Namely, in conclusion, when observed, the quantum loses its wave-like nature and manifests particle-like behavior. Wave-like means the quantum passes through both the right and left slits simultaneously. Particle-like means the quantum passes through either the right or the left slit exclusively. This slide shows the example of an experiment that verify the double-slit experiment presented in recent report. Here is a double slit. And the plain monochromatic wave is incident to it, like this. When the objective lens is defocus condition, left one and right one, where the light can be distinguished between the green path and the red path, no interference pattern appears. On the other hand, if the light lens is in focus condition, middle one condition, where the light cannot be distinguished whether coming from the green path or red path, interference pattern appears. Therefore, this experiment evidences photons, quanta, namely quanta, possesses both the particle and wave nature and wave particle duality of quantum. Here, as a short break, I would like to talk about a very famous story in quantum physics, Schrödinger cat. This is a kind of a thought experiment, namely, not really executed, but considered imaginary experiment. Inside seed room, if the sensor senses a radiation, the cat is killed by poison gas. Since the probability of detection is 50 by 50-50, the cat should exist in a superposed state of dead or alive. However, Einstein and co-workers claim that it is impossible to represent physics in terms of probabilities. So-called God does not play a dice. After extensive and exhaustive debate as well as enormous experimental result for quantum physics, we are left with two possibilities. One is a Copenhagen interpretation, which describes physics phenomena can be described by probabilities. Another one is multi-world interpretation, which considers what we observed is only only one aspect of a vastly branching reality. There is essentially no alternative beyond these frameworks. Okay, let's move on to another quantum topics, delayed choice quantum erasure. But this talk might be more complicated and mysterious than mentioned before. As mentioned before, when we observed which path the photon pass through, the particle behavior appears. Accordingly, one researcher considered what happens if we observe the photon after it passed. This experiment is so-called delayed choice quantum erasure experiment. A laser beam is incident into a double slit. Here. And the output beam pass through a nonlinear crystal BBO. That one. BBO has very important role for this experiment. When a single photon enters BBO, it emits two photons, which has a half photon energy of the origins. Then, in the case of red path photons, one reaches detector 0, D0, here. The other come across the beam splitter B. えー this one. Since the beam splitter works as a reflector or transmitter with a ratio of 50-50%, there are two cases that it is a reflection and detected by D4 here, and is transmitted to the mirror B here. After mirror B, the photon comes across the beam splitter again. In the same way, reflected photon reaches D2 and transmitted one detected by D1. Or in the case of blue pass, one of the photon pair is guided to D0. And the other comes across the beam splitter A. Yeah. At the beam splitter a half of the photon are detected by D3, and the others are transmitted to mirror A and comes across the beam splitter C. Get one. Then the half of them are detected by D1 and the others by D2. To sum up, it can be concluded photons detected by D4 obviously pass through red path, and one detected by D3 pass the blue path. That means distinguishable case. On the other hand, photon detected by D2 or D1 cannot be distinguished which path they experience. That means indistinguishable case. Here, the parallel worlds emerges. In the case of a distinguishable case, surrounded by green square, there is no interference fringe appear. While in the case of indistinguishable case, surrounding by brown square, interference fringe appears. The next slide shows a core of what makes the experiment so strange. The photon heading towards D0 should not know yet whether its partner photon will end up at D3, D4 or D1, D2. This result can be explained by considering the photons somewhat to time travel to the past when it's separated from its partner, or time travel to the future when it is detected at D1, D4 and transmit information. But it will never be possible. At present, it has been interpreted quantum system encompass two coexisting worlds, of which we perceive only one, so-called parallel worlds interpretation. Okay. This slide shows the outline, the overview of quantum optics. A quantum state is preserved only when it remains unobserved in an indeterminate states. The moment it is measured, the quantum state is destroyed, allowing a classical description. A quantum state appears to consist of two coexisting worlds, a superposition of state, often referred to as a parallel world. However, we can express these two worlds only in terms of probabilities. This concept has given rise to numerous anecdotes that have puzzled physicists, such as Schrödinger cat, God does not play dice, and the photon trial. By the way, a BBO non-linear crystal was used in delayed choice quantum inertia measurements. To reiterate the principle, it was responsible for generating two photons with half the energy of one photon. Because these photons are correlated with each other, they are so-called quantum entangled photon pair. Furthermore, even if the photon pairs are apart from one another, that is, also D0 and D1, D4 are far apart. Once the state of one photon is determined, that of the other is simultaneously determined. Accordingly, we infer such entangled photon pair could be used for application of remote sensing, remote operation, and communication without information carrier. By the way, quantum entangled photon pair applicated experiments won the Nobel Prize in Physics in 2022 for these three physicists. Okay, let's move on to the application edition. Before discussing the application of quantum optics, I'd like to explain polarization and quantum bits, so-called qubits. This left-hand figure shows the polarization states of photon as a globe, so-called Poincare sphere. On the north pole corresponding to right-handed circular polarization and south pole left-handed circular polarization. On the equator, it represents linear polarization, the others elliptically polarization. The light up animation represents linear polarization of minus 40 degrees, and the light down, the left-handed circular polarization. In the linear polarization, S polarization and P polarization are in phase, like this. In the circular polarization, they are orthogonal, like this. Okay. This slide shows the fundamental principle of photon quantum bit. As can be seen from the figure, Bloch sphere that express the quantum state can be represented by the polarization of photon. Therefore, any quantum bit, namely qubit, can be represented by the polarization state of photon. This slide shows an overview of quantum entanglement. Two states of each entangled photon are superposed, that is, superposition of 0 and 1, that means qubits. For the case of a photon qubit, superposition of right-handed and left-handed circular polarization correspond to linear polarization, like as rotating coin. By separating the photon pairs into separate locations and observing the quantum state of one photon, information is instantly transmitted to the other photons. To put in extreme cases, even when one entangled photon were placed on Earth and another one on Saturn, determining the state of one would instantly determine the state of the other. Therefore, by utilizing this phenomena, it is deduced remote medical care or something like that can be realized using entangled photons. Okay, let's examine how it's being applied utilizing the quantum light. First, I'd like to introduce quantum imaging, so-called ghost imaging. Why is quantum imaging called ghost imaging? Because the light that is far away from the object produces the image of object. What? It sounds incredible. I'll explain the principle in detail. NL denotes nonlinear crystal that emits two photons with lower photon energies than original ones. That means down conversion. And D denotes dichroic mirror that has operation of division into two passes depending on wavelengths. Laser light is separated at the beam splitter. And G1 is incident to the NL1. And the other is to the D2. The reflected light from D1, namely red path D, is illuminating the object. And incident to the D2. And at NL2, light path of path B is down converted, and hence the path F includes path D and down converted path D. At D3, red path F is being discarded here. But surprisingly, camera G and camera H reproduce the objective image. In contrast, camera C cannot. In addition, if we subtract image G to image H, further clearly constant image was produced. Let's consider the framework of this technique. It is obvious only the light from the red path D is passing through the object. But the interface light from the yellow path reconstructs the image. It can be inferred because it is impossible to distinguish whether red path F was generated in NL1 or NL2. It can interfere with yellow path E. Therefore, the yellow path E got information of object. As a result, after interference with yellow path C, the camera G and H constructs the image. Although it seems very weird phenomena, this can be said to be an epoch-making imaging method that cleverly utilizes the properties of quantum mechanics. Let's move on to the application example 2, quantum cryptography. First of all, I'd like to talk about the one-time part. Recently, when you log into social media and so on, you may hear something like, we've sent you a 6-digit authentication code via short mail. It is that. Although the one-time password is only 4 or 6-digit code, the reason why this password is very strong is based on use it only once and throw it away and set a time limit For example, 10 minutes. Since it is very difficult to intercept or decrypt password in a short time, one-time part is regarded as a strong encryption method. However, an issue has been aroused that it is difficult to transfer the one-time password, namely encryption key, safely. To address this issue, a method was devised for sharing en encryption keys using quantum cryptography communication. This slide shows the concept of BB84 being one of the quantum cryptography method. In the case of BB84, a single photon source where a kind of quantum light. It emits one photon for each time, is used as a light source. Sender Alice randomly select horizontal vertical polarization hereafter plus base or plus or minus 45 degrees polarization hereafter X base. And also 0,1 value is assigned for each base. Here 0,1 corresponds to vertical horizontal for plus base. Plus 45 minus 45 degrees for X base. Receiver Bob also randomly selects the base. However, if Bob's filter doesn't match Alice, the chance of getting the correct answer is 50%, 50%. This chance is absolutely guaranteed based on the principle of quantum mechanics, uncertainty principle. Therefore, the possibility of correct answer for eavesdropper is 3/4 for each photons. The value of 3/4 seems to be not so small. If we use plenty of photon, the probability of correct answer goes down by power of photon numbers, namely 3/4 to the power of nth photon number. For example, by sending 100 photon, the possibility becomes approximately 3 times 10 to the minus 13th power, which is almost impossible probability. Recent years, a quantum cryptography method has been newly proposed, which uses not single photon, but quantum entangled photon, leading to further secure communication tools. Finally, I'd like to introduce the quantum computing as a last application example. In 2019, famous scientific journal Nature released an article on quantum computer. It is based on superconductor qubit, and it was reported that a calculation method was completed within several minutes, where it should take 10,000 years if a supercomputer carries out that calculation. That is to say, quantum supremacy. Regarding the basic principle of quantum computing, a classical computer executes the calculation by switching 0 and 1, whereas a quantum computer uses qubit where 0 and 1 coexist. Therefore, one qubit accelerates the calculation twice, 2 qubits by 4 times, 3 qubits by 8 times, and so on. Although superconductor qubit needs a cryogenic cooling system by replacing photonic qubit, a room temperature operation quantum computer is realized. Next year, to the above mentioned press release, an article on quantum computer using photon qubit have been published in the scientific famous journal Science. In the field of quantum computing, progress in quantum optics technology is also noteworthy. This concludes my special lecture. Thank you very much for watching. I hope this lecture has sparked your interest in the fascinating world of quantum physics. For the latest information on our laboratory, please visit our website. Okay. Thank you again.